Lesson 4, wave properties, refraction, diffraction, and superposition. I'd normally start off by showing a little trick here. Basically what you do is get a mug, stick a coin at the bottom and just move your eye so you can't quite see the mug at the bottom of the coin. And then what you do is you carefully pour water in, and lo and behold, you can see the coin. Okay, now this is because the light bends as it goes from the water to the air, so it appears that the coin is shallower than it is. This is called apparent depth. Now we're just going to look at why this is. I think you probably remember this from year 11. This is because waves, when they change speed, bend. So for example, water waves travel slower in shallow water, so when they go from deep water to shallow water, they change direction. A common way of thinking about this that's used by physics teachers the world over is to imagine soldiers marching on pavement. When they march on the pavement, they can march fairly quickly, and then when they get to mud, they slow down. Now you'll notice the columns of soldiers. The columns of soldiers. Oh, they're still there. As they come down, this soldier here will slow down first. Okay, but the soldier on this side keeps going at the same speed, and it has the effect of changing the plane of orientation. Okay, so instead of being there, okay, because this side slows down first and that side slows down second, it has the effect of changing the direction of the waves. Okay, this happens, of course, not just with water waves or light waves, but all waves. Okay, in sound waves, you can see here, sound actually travels fast in warm air. So the sound waves leave the trumpet player here. The sound waves up here travel faster, so they bend around. The sound waves down here get stuck in the cold air, so they get slowed down here, and it bends the sound round in this direction. Okay, if you get the other way around, okay, so the sound here gets stuck in the cold air, moves slower there, so it has the effect of bending the sound waves in that direction. Light waves do this, of course. I've often tried to do this with some glasses, but I think you have to have exactly the right shape there. Okay, now let's just cut the PowerPoint for a second. Let's have a look at a ripple tank simulation of this. Okay, this is an electronic representation of a ripple tank. Here are the waves going along here in the deep water. When they reach here, the shallow water, they slow down, and you'll notice that this side slows down first. This side continues at the same speed and has the effect of changing the orientation of the waves. Let's see if we can just speed that up a little bit, the frequency, to make it a little bit clearer to see. Okay, so as you can see, the waves, as they enter the shallow water bend, they get closer together. You'll notice also there's some reflection over here as well. Okay, but we're really concerned about these waves here that have slowed down, changed direction, and they've got closer together, so the wavelength has got smaller. Okay, let's go back to here. Okay, so there is a relationship. Okay, now here we've got our ray here. Remember, the ray shows the direction that the energy travels. Remember, the wave front, of course, will be across 90 degrees to the ray. Okay, but we're interested here in rays. This is the angle of incidence. That's the angle that the ray hits the boundary. Notice we always measure angles with a normal. This is the angle of refraction down here. Okay, and there's a simple relationship, or not so simple if you don't like sines and cosines. This is called Snell's law. The ratio of the speeds in the different substances is equal to the ratio of the sines of the angle. So the speed of the wave in the first substance divided by the speed of the wave in the second substance is equal to the sine of the angle of incidence divided by the sine of angle of refraction. You don't have to know where that comes from. You used to do it, you don't have to anymore. If we're going, and we only use Snell's law when we're talking about light, so I should have mentioned that. So this is just light. If we're going from vacuum into the medium, this ratio is called the refractive index, and essentially it's the same when you go from air as well. The refractive index of air is 1, basically the same as a vacuum. So in the laboratory, we don't have to worry about going from air into glass. It's pretty much the same as from a vacuum into glass. Okay, so the speed of light in a vacuum divided by the speed of light in the medium is called the index of refraction, the refractive index. Okay, now you might have two different media. Okay, so if the refractive index of media 1 is n1 and the refractive index of media 2 is n2, then the sine of the angle of incidence, the sine of angle of refraction, remember, is the ratio of the speeds of the substances, the speed in 1 divided by speed in 2. Notice here it's now reversed. Yeah, that it's the refractive index of 2 divided by the refractive index of 1. Okay, be careful there. That is sometimes notated like this, rather confusingly. The refractive index going from 1 to 2 is actually the refractive index of 2 divided by the refractive index of 1. Yeah, physicists always making it clear. Okay, just remember then, okay, the wavelength changes, yeah, because the waves are slowing down, they get closer together. Okay, obviously the speed changes, they get closer together, but the frequency stays the same. If you think about it, it has to be true. You know, the number of waves entering the glass must be per second must be the same as the number of waves that are leaving. So the frequency stays the same. Just remember, if the angle of incidence is 0 degrees, the light ray doesn't bend at all. Okay, here's a rather nice picture there. This is on the International Space Station. I think this is a water bubble with an air bubble trapped inside of it. We could spend quite a while trying to figure out why he's upside down in here and right way up here. That's pretty cool. Okay, in the classroom now you do a practical to measure the refractive index. Basically what we do is we shine a beam of light into a semicircular glass block, measure the angle of incidence, measure the angle of refraction, calculate the refractive index of the glass. Notice, because we're shining to the centre of the semicircular glass block and it comes out along the radius, that it doesn't bend here, because it's leaving the glass at 90 degrees along the normal. Okay, in class you do some refraction questions. We're not going to do this here, but if you want to copy the worksheet, go to my website and you'll find it. Okay, that's refraction. Now let's have a look at diffraction. Okay, this is the spreading of waves when they pass through a gap or an aperture, or when they pass an edge or an opening. Okay, and the amount of diffraction is greatest when the size of the aperture is approximately the size of the wavelength. So you can see down here we've got a large aperture, much bigger than the wavelength, so there's a little bit of diffraction at the edges. Oh, sorry, let's go back. Okay, here we have a gap here that's of a similar size to the wavelength. We get a lot of diffraction. Here's another example here. Okay, you can see waves here passing through an object here. Because the object is a similar size to the wavelength, basically more or less the waves, by the time they've gone a few wavelengths past, join up again. Okay, I suppose this is a bit like if you hold a hair up in sunlight, you don't see the shadow. But here, because the object is much bigger than the wavelength there, we get that straight edge. Okay, another example there. Let's see if we can see this in the ripple tank, if it's still going. Yeah, it's still going. Let's look for diffraction. I think it's near the top. Single slit. Okay. It's here, so there's waves hitting the barrier up here, and they're spreading out. We'll talk in just a moment about that slight pattern. Can you see there that it's strong in the middle, and then weak there, and then strong there? We'll have a look at that in a second. Okay. Okay, well, in fact it's there. High-level people are going to come back to this next year, and we're going to see, in fact, that the waves don't spread out evenly. In fact, there's a central maximum, then a minimum, then another maximum. Let's see if we can go back to that ripple tank again. Okay, can you see that? There's a central maximum here, then there's a minimum there, where there appear to be hardly any waves, then there's another maximum there, and then a minimum, and a minimum, and a maximum. But high-level people are going to come back next year and look at that again, and learn about this formula here. Okay. Okay, diffraction explains quite a few things here. It explains really why when we listen to distant traffic, we tend to hear a low rumble, because it's the low notes that bend most around buildings and walls, so we can hear the low notes. The high notes tend not to bend so much, okay, because it's a smaller wavelength, and so we don't hear the high frequencies basically. Okay, radio waves diffract a lot, which is why we use them, of course. They're nice long wavelengths, so they diffract around most objects. Okay, time for a worksheet. Can't remember why I use this GIF now. I was thinking it's just a guy screaming because I'm in the worksheet. It's cool. Okay, and finally, superposition. What happens when waves meet each other? Well, before we go further, we can actually see here, we've got two waves here. We've got this blue one here. We've got this, I think it's meant to be green. It's not very clear. And what happens is they add together. When the two peaks meet, this black line is the resultant. When a peak meets a trough, they cancel each other out. And this is called superposition. Okay, this is the principle of superposition. It's a definition you have to learn, and many questions start with state the principle of superposition. So when two or more waves meet, the resultant displacement is the sum of the individual displacements. So the waves add together. Don't forget, of course, the displacement could be negative as well. That's how waves can cancel each other out. Okay, if the peak of one wave meets the peak of another, and the trough meets a trough, the peaks add together, the troughs add together, and we get a bigger wave. This is called constructive interference. However, if a peak meets a trough and a trough meets a peak, the waves cancel each other out. This is called destructive interference. In general, those of you going to study physics at university, we can make any shape we want by adding waves together. This is something called Fourier analysis, very useful to physicists. A beautiful piece of mathematics. Some of you may learn it later on in your physics careers. Okay, in class now we'd find out what happens when we add waves together. This is an interesting example here. Here are two waves that are almost the same frequency. And when we add them together, we get this. Yeah, we get a sound that throbs, really loud, soft, loud, soft. Guitar players will know this when they're trying to tune strings and you have two strings that are almost the same pitch. Okay, so interference patterns. Let's go back to our ripple tank here. Okay, now let's try what happens when we have two sources. Let's have a look. No, that's not the one. Let's have a double slit. So what happens when waves meet? Well, as you can see, we get this pattern. Okay, again in the centre we get this, what we call a central fringe of constructive interference. And then we have destructive interference here, and destructive interference here, and then constructive interference here, and constructive interference here, destructive. These are called fringes. Now, why does this happen? Well, it's all to do with something called path difference. Yeah. Okay. When the waves meet each other, if one wave has travelled half a wavelength more than the other, a peak will meet a trough, and a trough will meet a peak. They'll cancel each other out. But if the two waves, oh sorry, I'm pointing to the wrong one there. Yeah, they cancel each other out. If the two waves either travel the same distance or a whole number of wavelengths, then the peak meets a peak and a trough meets a trough. You get constructive interference. A little animation here. I don't know whether it's going to work. Yeah. Okay. So we can see we've got two sources here. They're in phase. Okay. Now, if we meet at this point here, this source is 8 wavelengths. Let's try and count that. 1, 2, 3, 4, 5, 6, 7, 8. This source is 6 wavelengths. 1, 2, 3, 4, 5, 6. Okay, so at this point we're going to get constructive interference because the path difference is a whole number of wavelengths. In this case, 2 wavelengths. This is what I'm after. Okay, so here are two sources, S1 and S2. They're giving out waves. Okay, the thick part is the crest of the wave. The thin part is the trough of the wave. So we're looking from above, really. And we can see in this point here, okay, that the path difference from S2 is 1, 2, 3, 4, 5, 6 wavelengths. The path difference from S1 is 5 wavelengths. It'll count that in a moment, hopefully. Come on, do it again. Come on, do it again. Okay, it's going to do it again. So here we are. Yeah, the distance from S1 to A is 5 wavelengths. 1, 2, 3, 4, 5. The distance from S2, as we've already talked about, is 1, 2, 3, 4, 5, 6 wavelengths. So the path difference is a whole number. We're going to get constructive interference here, and in fact, we're going to get constructive interference there, and there, and there, and there. So all the way along there, we're going to get a fringe of constructive interference. Okay, we call that an antinode. Okay, however, at this point here, the path from S1 is 3.5 wavelengths, the path from S2 is 5 wavelengths. That's not a whole number, so there